Okay, we're live. And let's remind ourselves what we're trying to do. So at a high level, we're trying to, take some data, output a model, output a predictor that will predict new labels correctly based on new features. And I'm going to repeat something that I've said a million times, which is that this ability to predict well on new features, labels correctly on new features, is hopefully been motivated enough now that this risk, this expected loss, is like a single number that kind of measures how well you're doing this. And the smaller that number is, the better you kind of are at predicting new labels correctly, new unseen labels. And so based on this data, our goal was to design this learner, which is just an algorithm that takes in a data set and outputs a model, this f hat, such that its performance on new data is small. That's our goal. And the procedure we use to do this is to minimize the empirical risk, which is this L hat term. It's our estimate of the expected loss. And if this empirical risk is close to the true risk, the actual expected loss, then hopefully this procedure will work well. And so what we saw in this whole optimization part of the course is that doing so we'll get to some empirical risk. And if we choose a more complex function class, then that probably means that there's going to be a function in there, a model, that better fits the data. And so our empirical risk can be made smaller. That is what this decreasing purple line means. We increase the complexity of the function class, we can fit the data better. And so our empirical risk can get very close to 0. However, what we saw in last class is that unfortunately, if your function class is very large, then what can happen is you can overfit the data set. In particular, when you have very little data points, such as in this picture, where you have only 5 data points. So when n is small, your function class is large, complex, then things like this can happen, where you overfit. And maybe I should put this word here. So what's going on here is that we're overfitting. I guess I don't need to put quotes everywhere. So you're overfitting. And visually, it looks like this when you actually look at how you're fitting the data, because when you get new points, you're not fitting it well. So you're overfitting to your data set. But this idea is summarized through this single number, which is how well we perform on new data and how well we performed on our data set. And what we see here is as the complexity of the function class goes up, unfortunately, the distance, the error between our empirical risk and the true risk grows. Okay, and this is the kind of story we saw, that unfortunately this error between the two increases, this difference, as the function class gets larger. However, it decreases if we make the data set smaller. Okay. And let me mention a couple more things, which, yeah, visually here we saw that this error is increasing. And the other thing we saw is that as we increase the data set size, this error gets smaller and smaller. So this was, you fix a specific polynomial degree, and you try to see, as you increase the data set, how small this error gets. And you can imagine doing this for every one of these points, and taking even the extreme, and we're going to be doing this kind of today, where we can take the extreme where the data set goes to infinity. And you might wonder, what is this kind of like asymptotic point for every single polynomial degree? Like maybe if you take n to infinity, this point is going to be like here, and here, and here, and here, or whatever. And we'll see what that kind of looks like. And in some sense, that tells us like the quality of our function class if we had infinite data, like what is the best possible fit. We'll discuss this more. Another thing to notice is that there's some like kind of interesting behavior, which is that if you increase the data set size, your empirical risk might actually increase because it's harder to overfit these larger data sets. So the way we've kind of described things so far, we have these like competing kind of things, right? Which is you want to make this error small, but if we compare the error between what we're actually minimizing and this, we see that, oh, well, this error is going to grow as we make the function class larger. It's going to decrease if we make the data set larger. However, if you make the data set larger, well, then your empirical risk might go up. And however, if you make the function class larger, well, then maybe this asymptotic point will go down. And we're going to see that like this behavior is kind of complicated between the two. And so we're going to decompose this into some like what are called more error terms that more naturally kind of model what is the error you're getting, for instance, from the specifically just from the function class, and then kind of what is the error you're getting just from having a certain amount of samples and doing estimation and things like this. It's going to be kind of what we're going to do today. But before we get to that, I'm just going to remind you about this whole test set and train set business, which is what this motivated is the kind of the story that, well, it seems like some polynomial degree kind of between a very high polynomial and a small polynomial is probably going to be like the best choice for you, or like when you're actually running your learning algorithm for like a fixed data set size. And then we talked about how would you actually do this in practice. Well, in practice, you only have a fixed data set. And so you will indeed get a curve like this when you run your learner on the data set. And we said, how do we get an estimate of its true performance on new data? And the idea was really simple. It was, well, if we just had two different data sets, one that we train on, one that we test on, the test set is not touched by our learner, it doesn't overfit, it doesn't even know what that data set is, well, then that data set, the test set, can be used to evaluate its performance on new data. And so, yeah, main idea, you take your data set, your original data set, you split it into two parts. So you take the first points up to the n minus mth point to be your train set, and then n minus m plus 1 till n is going to be your test set. And in other words, your data set, which was originally of size n, is now broken up into a data set of size n minus m, which is your train set. If n was like 1,000, maybe m is 200. So here your train set would be 800. And then your test set would be like 200 fresh data points that you can evaluate your model on. Okay. And so, yeah, and then we plotted these two things. And so what we saw is like the training error, which is what we've been seeing up to this point. Everything we've been talking about is exactly this like training error, training loss. It's the empirical risk on the training set. All these words are the same. Is, as we saw, it decreases as you increase the polynomial degree. However, when we try to evaluate how it's doing on new data, we see this kind of behavior that we saw above. Which is, you'll probably see something like at the beginning, it's quite poor, and then it gets better, but this error between these two things kind of on average should be getting larger and larger. But once again, for a particular data set, this can fluctuate. So you might see that here, this one actually dropped lower, this one went higher. And that's because you just have one sample of one data set here. And so in your next assignment, you will indeed see this. When you're dealing with one data set, you'll see this kind of not so smooth behavior like this. But when you do it over a bunch of data sets, which you can obviously do when you're simulating things in code, you will actually see this kind of smooth behavior that on average, this is the kind of behavior you see. And that just says that like, this is kind of what you should expect your learner, how it's going to behave on average over data sets and so on. So anyways, in practice, you do only have this one data set. You do this kind of train test split, and you would pick this point that has the smallest error, the smallest empirical risk on the test set. Okay, there's one more thing I wanted to mention relating to this. So in practice, you might hear about people splitting their data set into three parts, one being the training set, another being like this validation set, and another being the test set. And so the reason for this, well, first let me tell you, the validation set that people usually talk about is the same thing as this test set we're calling here. So this validation set is used to pick between different what are called hyperparameters of your algorithm. Okay, so let's just briefly jump back to what it looked like in optimization world where we had pseudocode. So in optimization world, like if we just look at an algorithm, like batch gradient descent, or mini batch gradient descent, there's a bunch of these different hyperparameters, right? There was a data set, and then there was like a learning rate, which you had to pick. And there was, okay, number of epochs, you'll probably fix that. But there's also like a mini batch size. And now we also saw for the polynomial case, we didn't write the pseudocode, but there would also be a degree p. And what we see is we don't really know what the right choice of like the degree p is, maybe what the mini batch size is, the learning rate. And each time you change these, you will get a different ERM learner, right? And you would literally need to rerun ERM using whatever your gradient descent thing. And each time you rerun it, right, you can rerun it for a bunch of different choices of these. And then the question is like, which one's better? And so this validation set, which we've been calling a test set from now on, is what is used to evaluate how each one of these, what are called hyperparameters, perform. So you could also have a different axis for learning rate and another axis for mini batch size and have all the possible combinations. And this is how it's done in practice. So it's called like hyperparameter sweeping. And you would have this one validation set that you've left out that you did not train on. And you would evaluate all of these different predictors or models you get based on all these different hyperparameters. Just like here, we're evaluating for a specific p. This would be like a hyperparameter. And then you end up with a bunch of different, values, and you pick the one that would be the smallest over all these different hyperparameters. However, now you've used this validation set to evaluate a bunch of different predictors. And the same story holds as kind of what was happening with the train set, which is your choice of hyperparameters is biased or kind of overfitting to the validation set. Okay, and so there's a third data set called the test set, on which if you want to actually tell the public or your boss or some like people that this is how I actually expect this final model that I got to perform, what you want is like a final untouched data set that nothing has been tuned, no hyperparameters have been chosen based on, just completely clean data set that nothing's been done on. And then you finally run the final model that you chose. For instance, this model, like this procedure here, you pick this, and then you finally have your third test set and you run it on that. And by run it, I mean, you just calculate the empirical risk on that final test set. And that number will usually be higher than this number because once again, this is like your kind of biased choice based on what did the best on this validation set. And then that is what you would give to like your boss or the public. You would say that we expect our model to have this kind of like error when predicting new points. Okay. And so once again, the reason there's this extra validation set is to kind of get rid of the similar issue we had with the train set, which is when picking your, let's say, polynomial degree, you are kind of overfitting to this validation set because you validate, you check this, 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 and this, and you might have just gotten lucky that on that validation set, this polynomial degree ended up doing better, but if you were to get a new one, you would do worse. Okay, and this becomes even more prominent, of course, if you have a bunch of hyperparameters, such as step size and batch size. You then have to take like, if you had like, I don't know, 5 different values for each of them, that would be 5 cubed, so you'd have 125 values, and you can see how that can get, bad. Okay, so that's just high level. Where in this course, for simplified purposes, we just have this test set, which does the purposes of the validation set, which evaluates the learner's model on different polynomial degrees. You can, of course, do this for other hyperparameters, and you get a pretty good estimate of the true expected loss or risk. Okay, but I just wanted to tie that into how you'll see in practice this extra step. And once again, just like that extra test set, that third set that you would have after the is really just to be able to present to the public or someone like, this is how I expect my predictor to perform. But that's it. That's just to give someone a quantitative measure. Otherwise, if you just want to like get the best model, this is enough. You pick this. This is your choice. You go run it. You know you made your kind of your best choice, and it's going to perform however it does. Okay. So that all being said, let's get into kind of a little bit more formally discussing how to decompose the error of the expected risk. So this is the risk, the average risk over data sets. And the idea is we want to kind of decouple a bunch of different effects or different error effects. And you'll see what I'm talking about, hopefully, as we go through a bunch of different terms that will appear. Okay, so the idea is, it's called decomposing the expected risk, right? This is the risk of the learner in expectation over data sets. And so we're going to decompose it into a bunch of different error terms, and this will somehow give us a little bit more insight into the effects of different things, like the type of features we have, the function class, the number of data points, how much more we should run our optimizer, and things like this. And you may have heard, and we'll get to it in maybe 30 minutes, this idea of a bias variance trade-off. And this is how we're going to, like, that's where the decomposition is going to give us one of the things. And people always talk about this idea of something's high bias and things high variance and things like this. Okay. So to introduce these things, we're going to need to introduce a variety of like different models. And we're going to kind of introduce them in this order of like, what is the best you can expect given like a certain amount of information for your problem. So we start first with the following case, which is, okay, so first we're going to start with, you know, this distribution. So you're actually given the distribution that the data comes from. Okay, so then the question is like, if you knew this, which you don't, of course, what is the best you can possibly do? And you haven't even, and we're also not even going to restrict ourselves to any function class. So if you just had a learner that could really minimize the true expected risk, or sorry, the true risk, which is minimize this thing, what would you really do? Nothing to do with data sets. You really just knew this distribution. You could explicitly calculate this. Well, we talked about this, which is this is what you'd really want to do. And you would just do this. You would just take the risk and you would minimize it. This is like best case scenario if somehow you knew all this information. And you would minimize it over all possible functions. We, of course, saw that this was kind of hopeless if you had data sets because of this no free lunch theorem. But if you really knew this distribution, you could expand this out as just an expected value, calculate it, and find the minimizer. And this quantity has a special name. Because this is, it turns out, the best you can do, right? Like you could never really hope to do better, because you're really minimizing the true quantity over all possible functions. And the name it's given is F Bayes, or the Bayes optimal predictor. Okay, so this is like the best you can imagine, and this is called like the Bayes optimal predictor. And one way to like visualize what this might look like is it's the function that somehow fits the data the best if you had infinite data points. And so this distribution, you can roughly kind of like visualize what it looks like by getting a bunch of samples, like as many as you possibly can. And you can kind of see by how many points you see in different regions, like the rough density or mass of these points. Of course, you can, this is in contrast to like explicitly writing out what this is. And so one way to visualize this is to plot like a super large amount of points, which maybe I will do, and you'll see this on your assignment. Maybe it's something like I just plot a bunch of them. Maybe they're like super dense around here, and then it droops down, something like this. And of course, this is just like a finite number of samples, but in your assignment, yeah, we'll do like an even larger amount of samples. And then you might see that if you could pick any possible function, the one that really minimizes this, let's say a squared loss, you were using a squared loss, might be something like this. Okay. And once again, this black points is, I'm just trying to show what it would look like if we had infinite number of points, just to give you an idea of what a hypothetical distribution might be. Okay. So this would be f base. And yeah, I suppose that, okay. Let's keep the colors the way I had. So this will be black. And that's f base as I have labeled up here. Okay, so first step. The next step is, well, we really limit ourselves to a function class, and we have a data set, but we're going to still keep with the case where we know the distribution perfectly, but we've limited ourselves to some function class. And the question is, what is the best we can do if we limited ourselves to this function class, but really could explicitly calculate this exactly? And that's going to be given a different name. And that's going to be like the best predictor or best modeling your function class. And that's often denoted by like f star. Okay, so let's maybe just scroll down here. So instead, so we have this. But the learner, which is a map from these data sets of size n to a function class, is now limited to a function class. It doesn't just output any possible function, it's limited to some function class. And for, I guess, the purposes of this, let's say it's limited to linear functions, which we denoted as f1. So these are polynomials of degree 1. Well, in that case, well, the predictor is going to be called the following, which is, we're going to call this f star. And just to make it clear, what's going to change is we're going to just take the same thing as the Bayes optimal predictor. And maybe what I should mention is the reason we're defining all these is because in a moment we're going to compare all of the different like the expected risk of all of these, and we're going to see that each of them produces a new error due to different aspects. So you can see the error of this thing is going to be due to the change in function class from considering all functions to a smaller function class. Okay. And so, yeah, this quantity here, we just take the same thing as the Bayes optimal one, but now we have changed the function class to be this f1 guy, which is what our learner outputs. Okay. So if our learner was restricted to this, this is like the best it can do. Of course, well, actually, I shouldn't even say that we have a learner. Maybe I should discard this. But we have to output from f1. Because we're not using any data set here. You have access to this, so just calculate this, minimize it over your function class, and okay. So what will that look like? Well, now you're restricted to a line, so the best fit you can probably do is maybe something like this. Okay, and that's f star. Okay, and then finally, the third thing that we've already been talking about up to now, which is if you know the data set and you're restricted to a function class, well, then you just do what we've been kind of doing, which is ERM. So now you don't, I guess, know this, but we have to output from f1, and we have a data set. And I'll call that data set like, here apparently I gave it name D1, and that data set, well, it's like we've seen up to now. X1, okay, we just have a data set D1. And then based on this data set, what we would do is do the usual ERM, which is we called f hat. And f hat would be, well, let me just make it clear how this compares to before. So all that's going to change is now we're going to still be limited to this function class f1. But we also now use the empirical risk, so based on data. So that's what this data set has now replaced. We can't explicitly calculate the expected value. We have to estimate it with data. Okay, and that gives us f hat. And the picture should be as follows, which is now you have some data set. Let's take some number of points, I don't know, let's say 5. So from now on, n is going to be 5. Maybe I put that so n equal, well, you'll see from the picture. So you might have like 1, 2, I don't know, 3, 4, 5. And then maybe your best line will be something like this. Okay. And so hopefully you can kind of see that there's already, there's different points of error that are being introduced. There was this like f Bayes, which couldn't even label the points perfectly because there's just some inherent error in the fact that if you fix some, let's say, number of rooms of a house size, there may be different prices for it. And then after that, if you restrict yourself to a function class, and you even knew the true distribution, you still have some error. There's some error from this green function to the black function, because you're not using every possible function. And then further, if you then restrict yourselves to using a data set and not knowing the true distribution, you can see how the data set might be an unrepresentative sample, or it could be representative but not representative enough of what the true distribution looks like. And so there's some error between this orange line and the green line. Okay? And I'm going to draw a few more things, but the idea is we're going to try to compare the expected risk between all these predictors to see how this error decomposes and what we can change to improve things. Okay, and there was just a question online, which is f Bayes represents the best predictor for an infinite data set, right? Yeah, and the answer is that's correct. So f Bayes you can think of as the best predictor when you do not restrict your function class, you pick any function, and you have an infinite data set, which is equivalent to thinking of if you know the true distribution because this thing is a weighted sum based on the probability of getting any single feature label pair, which is exactly the same ratio. That weighting would be the exact same ratio if you had infinite data. Okay, so that's really the best you could ever imagine to do. And I mean, a natural question you might ask is okay, well, in this case, f star, if you restrict some function class and you have this true thing, what does this function look like? Because we could calculate it, and we're going to see that that's going to be we're going to see that in a couple lectures, that that's another approach to solving these kind of problems that's not quite ERM, but we'll see it's actually turns out to be equivalent. Okay, we'll talk about that. Okay, so let's get back to the story. The other thing I want to mention is so I pointed out in this example that this, let's call this data set 1. So this is one particular data set. You can imagine if you went out and gathered a different data set of 5 points, it might look different. And since it might look different, which I mean, it very likely will look different, you're probably going to get a different predictor. So if you went out and gathered data set 2, maybe it looks like this. And then maybe the best fit line for this kind of thing is like this. And so, yeah, so that's possible. And then you can see that clearly as the data set changes, your predictor will also change. Okay. And yeah, that's really all I kind of want to say about that. I mean, another thing we can observe, okay, we can do one more plot. So that's if you vary the data set, of course, okay, some other things to observe is if you change the data set, the only thing that's changing is your predictor that you're outputting based on the data set. F star does not change. It has nothing to do with data. F Bayes also does not change. The data set only affects what you predict. We can also think about what happens if we change the function class. So now suppose we have a bigger function class, let's say f2 instead of f1. So we have this set of all polynomials up to degree 2. Well, what would change is now f star would likely be not a line, maybe it'll be something like that. I don't know. Maybe that's a slightly better fit than a line, that quadratic. And similarly, the purple and the green data point predictors might now also look slightly different. Maybe this is a better fit to the orange ones. And this maybe is a better fit to the purple one. Okay. So that's, and maybe I'll do one more example. So the thing to notice is now if you, of course, increase your function class, your f star is getting better, right? It can get closer to f base. Hopefully you see that. And you can also see that, of course, like now your predictors can also, they're using the same function class, they can get better. But to exaggerate the point of what I'm trying to make, we're going to see how making this function class larger actually affects your kind of error between f star and your predictor in the following way, which is, let's now suppose we chose a really expressive function class. What did I say about, yeah, suppose we use f10. So let's suppose that like you can exactly match f base, like the perfect predictor. So the Bayes optimal predictor is actually in this class. So I can put that, and f Bayes is an element of here. So f star can equal f Bayes. That's the best predictor. So now you get this overlap thing, which is they're the same. And maybe I just draw that right beside each other. So here you would have f star is equal to f Bayes. So there's no error due to your function class. Your function class is expressive enough. How does this look when you try to fit your data points now? Well, it might start looking something like this. And the purple one, well, maybe it looks like this. Okay. So what you see is that, well, now you can start experiencing very large error between the purple and the green function because you have a very large function class and, well, not many data points. So function class helped this green line get closer to f Bayes. The f star gets closer to f Bayes. Right now we're still building like intuition, but f hat, which is the thing you produce, can really, well, we have seen overfit and can be quite far from f star. Okay, so this function class is unfortunately going to kind of hurt us when we try to work with data. And another thing you might notice is that as you change the data sets, the actual predictions your learner will output can be very different. Like this orange function can be very different from the purple function. While in the case of lines, you can see they don't vary that much. Okay. Okay, so that's just a bunch of like kind of observations. Now let's make this a little bit more accurate. So now we at least have the formal definitions of a bunch of oh, and maybe I can give some names to these pictures again. So this, what's happening here is like what we've seen before, which is this is overfitting. This is where your function class is very expressive, but because of that you overfit the data. Well, under here your function class is probably not expressive enough, and you can't quite represent what you want, which is something like this. So here you would have underfitting. And we'll make this a little bit more precise soon. Okay, but the point is you should kind of be able to go between these plots of the expected loss and the empirical risk, or from these plots when you're fitting data, and understand where underfitting and overfitting and stuff like this happens. Okay, so now let's move on to decomposing the error terms. So one way to think about this is as follows. Let's draw this. So you can imagine having like just a one-dimensional plot, let's say, where down here you have 0 error. Okay, this is the 0 bar. And then you can start talking about how does the Bayes optimal predictor do? Like how much error does the Bayes optimal predictor have? So that would be like the risk of f Bayes. And that has some error, okay? We're going to give this error a name. But before that, let's just kind of build up all the other error terms. So this is really roughly speaking, this is going to, well, actually, maybe let me give the names now. So what is this error coming from? Well, this is the error due to like the fact that just there's inherent randomness or noise in the labels given a particular feature. So maybe you know the number of rooms of a house, the distance to downtown or something, but still for that particular specifications of a house, there may be very many like different prices for that house. And so no matter what, you can't really avoid that error unless you go out and gather like more descriptive features. Maybe you can gather exactly the type of like materials the house was built in and the year it was built and like all this type of stuff, and that'll kind of reduce this error. But oftentimes this kind of information is not easy to gather, and people call this kind of the irreducible error, because this is usually not in your control. Usually it's like some fixed information that you're only able to get from like your users or the people you're surveying. And so this is like inherent error that you really can't get below. Okay. Then comes another error term, which is the error due to your choice of function class. And so, of course, if you restrict yourself to using a smaller function class than fbase belongs to, as we have seen above when you had to use a line, but fbase was like this curve, well, then you end up with another error, which is the error between f star and fbase. And f star, we, I guess, used the green color, so I'll just put green for it. And that's another error. And that's the error due to what is called like the function class you use, or the approximation, the function approximation you end up using to represent your predictor. And so this has a name called the approximation error. So this is the approximation error. And that's the error due to the function class choice. Okay. Then after that, we actually make a choice of a predictor, right? Based on data. That's like what our actual choice is. So, right, our actual like ERM learner will have the same function class as f star, but it doesn't have access to calculating this expectation explicitly. It needs to use data. And so that itself has some error, of course, due to using data, due to it being an empirical, minimizing the empirical risk. And that's the error compared to, like, let's say our f hat function. And that is called the error due to estimation. So it's called the estimation error. And that's all we've seen in the plots above. And that's usually all that's kind of talked about in this stuff. And we're not going to need to know the next one, but it's worth mentioning, which is, you can imagine there's one last bit of error, which is that in reality, you never solve for the true minimizer, as we've been asking here, right? We don't actually get the argument of this if we're using, like, let's say, batch gradient descent or things like this. You'll probably stop at some point, or you might have not chose a good enough step size or things like this, right? Unless you use the closed form solution, of course. If you use the closed form solution, you do get this. But in general, if you're using gradient descent, you might not run it for long enough. You might not quite get to the minimum. And so that's an error due to your optimization strategy, right? And so, yeah, there is, people will talk about this. We're not going to talk about this term in this class, but I will just mention it, which is there's going to be one last error, which is what you really output. And maybe I'll give that a color of blue, which is you'll output something like f hat, and I'm just going to write it here like in notation that I don't describe, but like maybe after t steps of gradient descent, so after t epochs. So this thing, of course, we think is going to be very close to f hat, but it might not be based on your choice of step size and so on. And so this last bit is like the optimization error. Okay. And this is what you really output. This guy here, it has some performance on new data, which is determined by the risk, the expected loss. And it has, I mean, some distance from zero, right? And this is the thing we're going to want to make small and so on. And you can see to make it small, hopefully this picture gives you a lot of intuition, at least I think it does, which is there's all sorts of places you can address the errors. And you can try to kind of like understand how much error do I have due to this, or due to this, or due to this, and you should try to like attack the lowest hanging fruit kind of. And we're going to get more precisely into what is exactly affecting each one of these, but it's kind of obvious, right? Which is like, here it's just like, the only thing you can do is gather more informative features. Because there's nothing to do with data, there's nothing to do with your function class. It's just like, if you're predicting houses based only on the number of rooms, there's probably going to be a lot more fluctuation in the prices than if you had number of rooms, distance to downtown, material of the house, age of the house. Then for a particular house with a particular set of features, it's going to be a lot less fluctuation in price. And that's this irreducible error. How do you minimize this? Well, clearly, you just change your function class. If you make it more expressive, more complex, this will be reduced. You move on to here. How do you make this smaller? Well, this has an interesting like relationship where increasing the data set will make this smaller, of course, because then your estimation, which is based on data, is going to get better. However, then there's the unfortunate thing that when you make the function class bigger, this gets smaller, but this can grow. And that has like a competing battle, which is what we've seen earlier, which is that like just right point, which it kind of trades off these two things. And then finally, there's the optimization thing, which you also have easy access to. You can like, well, you don't have access to this, but you can estimate it using the test set. And you can kind of see that as you run for longer and longer, whether you're getting smaller and smaller and how much error you're having here. And the way you reduce this is to just choose better step size, use like a better mini batch size, run for longer epochs, and so on. Try to get to the minimizer. And so, yeah, these are the various points of error that you can try to address. Okay, and let's make that even more formal. So people will often rewrite this as the following. So we're going to forget about that optimization error part, and we're just going to think we always got the max. Yep. So the closed form solution will have 0 error here. This is strictly due to how you're optimizing and stuff. And in practice, you will never get a closed form solution for any like big enough problem. Yeah. Okay. So this is the thing we want to, well, really want to make this small, but we're going to just assume we have the closed form solution for this lectures, which is kind of classically how it's done in machine learning for now, and we know how to make this smaller. So we're going to care about how, like, what's the value of this, and we're going to decompose it into these different error parts. And the reason I drew this picture first is because the math is probably going to look really funny, but it should now make sense, which is, this is what we care about. We care about making this error small. And now let me write some terms first. So just so we can have everything in one place and not forget, we have fbase, which is the following. Okay. Then we have f star. Okay, maybe I make this a little bit smaller. And then we have f hat. And for writing this, I'm going to add one extra like subscript, which is to indicate that f hat really does depend on data. And if the data set changes, then it changes. I'm going to subscript f hat with a d for the data set like we've been doing before. And that makes it clear that this term depends on the data set because L hat is calculated based on it, while the others do not. And so here, that's why we have this expected value outside. So this is the average expected loss or risk of our predictor averaged over different data sets. And we've seen this above, right? That's because, look at this. One data set, you have this kind of error. Another data set, you have this error. So how do we compare between them? So we need to average over them. Of course, we're not going to need to do that for f star, and we're not going to need to do that for f base, as we'll see. Okay, so now let's decompose this into the error terms we've seen. And the way this is done in math is you just add and subtract a bunch of terms which are just introducing 0. So we have this term, and now from it, I'm going to just add and subtract the same term, but with f hat replaced with f star. So in here, I'm going to put f star. Then I'm going to notice, so I'm going to add and subtract this. This has changed the equation, not at all. I've just added and subtracted the same thing. I've added 0. But now we can talk about the error between these two terms and the error due to this. The other observation is that f star has nothing to do with data. So an expected value of a constant, and the expected values over the data set, is just the same thing as the constant. So you can take that out. Okay. Next term is this, and now we want to compare this to f base, so we're just going to go through the same procedure one more time and add and subtract f base. And this is just mathematically kind of expressing the same thing we saw above in that picture. And this is called like the approximation and estimation error decomposition of your expected risk. And now these terms are exactly what we had called earlier. So this term is your estimation error. I guess I'll call it EE sometimes. This term is your approximation error. And this guy was the irreducible error. Okay, and now I'm gonna, in words, kind of write out some different, like what we already discussed, just to make it clear, which is like, how do we address any of these things? So what affects each of the errors? So like, yeah, what affects the errors? And we're gonna go one by one and kind of write out some points. So first, the irreducible error. So how is this guy affected? Well, really, okay, the idea in English is like this is due to inherent noise in the labels. And it will decrease, or maybe I should write can decrease. It won't increase, at least. Can decrease if you gather more informative features. Okay. Of course, if you gathered, like if you had distance to downtown in miles, and then you gathered distance to downtown in kilometers, you gained no new information, and you gathered new features, but it's not going to change. So doing things like that will not help. And the other question is like, is approximation error the error of this relative to 0 or this relative to f base? And here we can see it is this due to f base, but here we can very clearly see that it is the difference between f star and f base. So we're really trying to break up, like, we're definitely not trying to compare everything to 0. The thing is, like, we want to break up the whole error. This is like our final result. This is our final error. We want to break it up into its like constituent parts, each coming from like separate things, which we can hopefully talk about and control. And so, yeah. So it's like you gain some error from here, and then like, okay, I gained this much more error on top of that, and then on top of that, I gained this much more error, And this is like very classic about talking about anything in math that's for like applied math, is like anytime you have any sort of like error, you try to break it up into like all of its constituent parts and control each one of those separately, because yeah, that's a lot easier. Yeah. Yeah, so here once again we should remember that here we have no like restraints on computation or runtime. You really are searching for the best function to fit this. So there will be no issues. I mean, adding like there's a difference between adding like bad features, which is maybe like repeated features that you have, and adding like features that are like maybe it's like incorrect features, or like they're just like wrongly labeled or something like this. But of course, when you add these features, your dimension increases, and so when you actually talk about like computing, for instance, f hat, the computation time is going to increase, and you might also need more data to fit it better. I mean, you actually will need more data. So for the same number of data, then this can actually also, where is it? This error can also increase. Because this estimate, like this is based on L hat, which we'll see in a second, that empirical risk, and the number of data points you need for that to be a good estimate will actually scale with the dimension of your features, which we don't talk about in this class, but that ends up being the case. So yes, that will affect things. Okay, next is the approximation error. This one's nice and simple. Which is like due to function class choice. And so if we were just to look at this, you'd be like, oh, I want to pick the biggest function class. And so this can decrease. And by can decrease, it means it will decrease or stay the same. Okay, maybe I should write that. Decreases or stays the same. This is, of course, it will stay the same if f base is already contained in here. So we already saw this. Like if f base is not a line, well, then there's going to be some error. But then at some point, you're going to make it expressive enough that f base, the best possible fit, will be in your function class, and then making it any more expressive will be kind of useless. And okay, maybe I'll mention one more thing, is like we talked about how this function class was like how we introduce like what is called prior knowledge, or people call it inductive bias, into machine learning. And from the no free lunch theorem, we saw that like this is going to be actually absolutely necessary, because if you don't restrict your function class, well, then the labeling function could be arbitrary, and you're going to need essentially infinite data, or as many data points as there is features in your domain. But if you have an infinite domain, it's actually you can't do it with any finite number of data. So you're going to need to make some choice on this function class. And this is like where you can see prior knowledge can come in. It's like, oh, somehow you knew that, well, f base, like your data is definitely not linear. Or maybe you did know it was linear. Well, then you choose that function class. And so if maybe you knew it was definitely not linear, well, then maybe you like choose a specific, maybe you knew it was like this. Maybe you knew for sure it's like some cos or sine wave. And so maybe then you would change your function class to these cosine or sine functions. And that might help you a lot, instead of trying to fit it with polynomials, which might be a lot harder, and things like this. So yeah. And I mean, if you really have perfect prior knowledge and you know what f base is, you'd just pick your function class to be f base, and you'd be done. You didn't have any of these issues with having a big function class and needing to search from it and so on. So yeah, hopefully that kind of helps with this. But yeah, so this will decrease or stays the same if you make f larger. And once again, this is like if you make f larger, this really means that the f becomes a superset of the previous f. If they have if one has functions that the other doesn't, then it's going to be incomparable for the purposes of this class. Okay, so yeah, maybe this deserves some more emphasis. Like, yeah, by make larger, it really means that the f you chose is a superset of the previous f. And in machine learning theory world, this can be like made a lot more precise in the sense that you can actually talk about like a function of the function class, which maps to a number. And the bigger that number is, the more kind of complex or more expressive the class is, and the smaller, the less expressive it is. And that will exactly dictate kind of how much data you're going to then need to actually get like a good estimate and so on. And this is like what, in some part, a large part of the theory world works on, is like somehow trying to describe the complexity of function classes in terms of how much data points you're going to need to kind of find a good function in that class. Okay. Anyways, let's get to the estimation error. So estimation error is kind of the trickiest of them all because it has the inverse effect for function class size. And so, yeah, this is due to using a data set. And it has, unfortunately, two kind of ways. So it can, let's see. Actually, yeah, it will, yeah, it can probably stay the same. Well, decreases or stays the same if n increases. Obviously, if your data set increases, then you get a better estimate of your empirical risk, and then you're actually minimizing something that's a lot closer to the true expected loss or the true risk. However, unfortunately, it will increase or stay the same if f gets larger. Okay. And we've already seen this kind of trade-off here, and that's what we've been seeing before about that like just right point, which is this battle, which is the approximation error will decrease if f gets larger, but the estimation error will increase if f gets larger, most likely. Okay. So ideally, yeah. Ideally, you want to pick a function class, like this is where you really want to use your prior knowledge. You want to pick a function class that's in some way the smallest possible, because you can see the smaller the function class, like, and it still captures f base, so it really captures what you want, then it's going to really help with the estimation error, because the estimation error won't be as large. And that should make complete intuitive sense, right? If your function class is really expressive, really complex, it's really easy to overfit. So you really want to limit it to be like kind of as little functions as there is possible that you really expect to properly fit the true underlying distribution, the true data. Okay. Okay, maybe I'll say one more thing, which is like in like modern machine learning, there's all sorts of these different like architectures that people use for neural networks. Maybe you've heard, you don't need to know this, but there's like these convolutional neural networks that add like a very specific structure to neural networks that are used for image classification and stuff like this, that make use of the way the world works. That like usually similar things are in similar regions, so it uses these like special, I guess, convolutional steps that like average over specific regions of photos and so on. And these are like specific architecture, or specific, by architecture I mean function class choices that we're using our prior knowledge of how images work in the real world to basically reduce the set of all functions we search to these ones that probably should work. And it's the same with like this large language model thing. We use these like transformers, which, I mean, we will actually sort of see at the end, but they also have a specific like style of function which can kind of like what is called attend or look back at all the words and compare them like pairwise. And this turns out to be very useful to like learn about relationships between words and sentences. And this is also a very specific function choice, a specific function class choice, which somehow seems to properly capture our inductive bias, our knowledge of how language works. And yeah. So you can hopefully see how like this choice needs to be made everywhere. Yeah. And the question, yeah, was a good, oh, I guess someone answered it, but I'll answer it again, which is like, why don't we use the biggest function class we possibly can? And the answer is, yeah, because this estimation error will go up as we see. It's going to overfit to the data set. Oh, okay. That's all I'm going to say about this, actually. This term, we've already seen. In the course notes, like the written up version, not the handwritten notes, it talks more about how you can decompose this error into the error we've actually been talking about slightly before, which is, notice this is the expected risk, but we really minimize the empirical risk. So what you do is you do like something that we've already kind of been seeing, is you add and subtract this kind of term. And this is the term, yeah, this kind of term. And this is the type of term we've already talked about. So you add and subtract it, and then you see, oh, the error that you get here is really the error that you have in minimizing the empirical risk relative to the expected risk, which has this kind of behavior that we talked about much earlier on, which is that these are often not the same and follow this type of behavior that when f gets larger, it increases and increases, and that's how it's related. And yeah, but you can, I guess, read about those details if you want. Okay, so what's next? Well, what's next is plotting this, apparently, which should also help a lot, because now it will kind of give us an idea of how close we can make those two lines that we saw earlier. So let's grab the picture that we've been working with last class, and let's fill in a couple more points and see what happens. And we'll have a more precise name for overfitting and underfitting now too, because they will correspond to certain types of estimation and approximation error. Okay, so here's our plot. I guess I will move this a bit up. Okay. So we had this line, which is the error due to, like, as the function class varies, of our actual predictor. It's like true expected risk, which is the term we started with. This is this term. And what we want to understand is, where is this error coming from? And we're going to draw these three terms now. So to draw that, we've drawn this already. We need to draw this term, and we need to draw this term, which is the error of f star and the error of Bayes. So first of all, let's draw f Bayes. So f Bayes, it doesn't matter what function class size you use. It doesn't matter what data set size you use. It's always going to be the same number. And that is, once again, the best you can expect to do. So that's probably not going to be 0, at least in this regression setting, right, with the houses and stuff. And so that might be somewhere over here. And so that'll be like f, the risk of f Bayes. So that'll be like a dotted line over here. And notice, this purple line can actually go below it, because that's minimizing the empirical risk. That's fitting your data set. You can fit your data set perfectly, but it might be the case that when you get new data points, like infinitely many of them, you just can't fit it perfectly. So, and this will eventually go, I mean, we saw this picture, which is this is going to increase as we get more data, because it's going to be harder and harder to fit it perfectly. I mean, and at some point, you're going to see the exact same feature with two different labels, at which point you will not be able to get it to 0. Okay. So that's f Bayes. Now f star, well, f star depends on the function class, and where the x-axis is over different function class sizes. So now we can see what is going to be like our best possible performance, assuming that we were using like the true distribution. We could really calculate this quantity perfectly. So first of all, it's got to be lower than this, right? Because here, this f hat was not chosen to minimize the risk. It was chosen to minimize the empirical risk, an estimate of this. So it's got to be some plot that's like under here somewhere. And that's what it's going to be. So it's got to be below this. It doesn't need to be above or below the purple line. It can be anything. So we can, I'll draw it. Yeah, I'll draw it here, but. And so it's going to approach f base, as we've seen. Because as the function class gets bigger and bigger, eventually f base, this function, the Bayes optimal predictor, will be in the function class, at which point it has 0 error, and onwards it has 0 error, because the function class, as it gets bigger, will just continue containing the optimal predictor. Okay. And that is this error. And it will depend on p, right? Change of the function class. Okay. So now we can look at those different errors that we drew above and see where they're kind of coming from. And so let's talk, we're going to talk, I mean, the irreducible error we've seen, or like we can see, this is the irreducible error. You can see it from anywhere. This is irreducible error. And should be clear. You're changing all sorts of things. It's literally not changing. You can't do anything about it. Unless we were to draw like another axis of like us gathering new kinds of features and seeing how this will work. But yeah, okay. That's the irreducible error. Now, what's next? Well, there's the error between f base and the green line, which is due to your function class, which is called the approximation error. And now I'll draw this line here. So let's do it for, let's do it here. Or how should I do this? So there's this error. Oh, it's up to the green line, sorry. So this guy here is the approximation error. And this guy over here, up to the green line, well, this is the estimation error. And similarly, we can do it over here, which we saw. So this was the underfitting case. And it's going to turn out that underfitting is characterized by small estimation error, but high approximation error. And this should make sense. Underfitting usually occurs when you don't have a big enough function class, when you can't approximate the data well, actually the true distribution well. And so that's when you underfit. You underfit when you have high error due to approximation and low error due to estimation. If you had high error to both, then it's just, I mean, it's neither of them. You're kind of, there's all sorts of problems going on. And then on the other side, you have the other case, which is, let's do this one, high estimation error, but small approximation error. And this is what overfitting looks like. Overfitting is when you have a really big function class, you can really fit the data well, you almost have no error due to approximation. However, you have a high error due to estimation. And this looks like if you change your data set, right? Okay, let's look at what the error is. Estimation error. This says, how do I differ in my empirical or my risk, my expected loss, on average over different data sets relative to this? Well, I can look at the picture and it's like, well, I mean, first of all, any one of these has probably a high error relative to the green thing. And on average, over data sets, you're still going to have this high error. Okay. So this will be how you should think of underfitting and overfitting. So I can just put that more precisely, which is underfitting will mean okay, so this will be the case when it's high approximation error. you can't approximate it well, you can't fit it well, low estimation error. Okay. And like, I mean, you know how to solve this problem. You increase your function class. Hopefully the estimation error doesn't go up too much. You can see here, we can look at the plot, you know. You want to solve the problem. Okay, let's increase our function class. Let's go to 3. Okay, nice. The approximation error went down. The estimation error went up, but cumulatively, it went down because from here to here, it's smaller. Then you can do it again, and it still went down. You're in good shape. Then you do it again, and unfortunately, now the approximation error is basically 0, is much smaller, but the estimation error has now grown enough that this total cumulative error is larger than before. And so there's this trade-off. Okay, I guess that's all I want to say for that one. Overfitting. Will be low approximation error, high estimation error, as we saw. Okay. Yeah, and we can draw maybe like kind of one more plot, which is going to describe the following. So far we've been just thinking about how the function class affects things. Here we have a fixed data set size, which was like n equal to, let's say, 100, and we took the average over all data sets of that size. Remember the error due to estimation, right? This error here is like, you can bring it down to 0. You can get it as close to this as possible if you make the data set as larger and larger. So what you should think of is that if I make my data set larger and larger, this point, this orange line, is going to get closer and closer to this green line. And similarly, this purple line, which is what we're actually optimizing over, is going to get closer and closer to this green line as well. Okay, so visually, we can actually take a previous plot and add in 2 more lines. So we saw this thing, which is the error as n changes for a fixed polynomial degree. And now we can throw in and add kind of, what is this approaching? And then we can see how this plot would look for different degrees as well. So as the data set gets larger and larger, it seems to be approaching some like value here. And that value for 4 will be this value over here. This will get closer and closer to this, and this will get closer and closer here. And that's just showing that we're getting to as best as we possibly can with basically infinite data for that function class. And so we can really now draw this point, which is what this is approaching. That's this L of f star of 4, because p equals 4 in our case here. Maybe I should just put p. And f base is still going to be where f base was. It has nothing to do with data set. And so this guy is still the usual L f base. Okay. And so data set increasing means that this orange and this purple, which once again, the purple is how you're doing on your data set, your empirical risk, you're evaluating that. Orange is how you actually do on new data. They get closer and closer to this f star. They get closer and closer together, which we've already seen before. But in particular, they approach this green line here. Yeah. And so another relationship, if you have really, really big data sets, you can see that you can start making your function class much, much bigger, because likely this orange curve will start to look much more like this. And it will start to only go up at a very later p, much later p. Okay. Yeah, so that's this thing, a little bit more detail. it turns out that this like approximation, estimation error, decomposition stuff is one way people like to talk about it. It is very nice and clean because it breaks it up into like the comparison of the risk or the expected loss between all these predictors. And another way people like to talk about things, which will be useful for when we talk about regularization in the next class, is this bias variance trade-off, which actually maps exactly to the estimation and approximation error we've seen so far. So that's nice. But when we're going to talk about regularization in next class, and we're going to see how it actually differs. So let me just give you the title. I'm going to write this out. So there's another way to decompose the errors into this like bias and variance. People talk about this bias variance decomposition. Maybe I should say that. And it has a very close relationship to this approximation and estimation error, but has like a different interpretation. So we start with the exact same thing as before. And yeah, maybe I write it out because it's not hard to write out. And then next class we'll talk about it more. So of course you still care about this. This is what I want to bound. I want to bound the performance of my predictor on new data on average over data sets that I'm going to get. First step, same as before, but I'm going to like make it into two steps. I'm going to add and subtract f base. So I'm going to compare it to L of f base. So I'm just not adding the f star part, which is totally fine. So I'm going to subtract and add. And so I still end up with this irreducible error term. And since I said we're not doing approximation estimation error, of course the decomposition is going to differ here. And so instead of comparing to f star, we're going to compare to a different quantity, which is going to be the predictor we output on average over data sets. So we've seen in that picture that if I change the data set, my f hat might be different. I can take the average predictor over data sets. And so, okay, there's going to be a quantity now, which we're going to compare to instead of f star called f bar. And notice the bar kind of is like the sample mean, the average. This is what it's usually called. This is going to be the average predictor over data sets. So I'm going to take my f hat of d. This is a function of x. This is this orange guy. Okay. And I'm going to take its average over data sets. Right? This expectation is going to be over data sets, conditioned on a specific input x. So this is the average value of my function at the point x. I just take it over all the functions, and then I will get a new function, which is literally take all the possible data sets, produce all those functions, take the average value at every single x point, you get a new function called the expected predictor. And that's what we're going to compare things to instead of f star now. And that's what I'm going to write above next class. But the other thing is this turns out to be approximately, and actually for everything we've seen above, exactly equal to f star. But with regularization, this is going to change. So for now, these are actually exactly equal. And we're going to see that the comparison will also be exactly the same. But then we'll talk about how it changes when we add regularization. So yeah, maybe let's stop here. So what we're going to do is we're going to kind of add and subtract the f bar version above. And we're going to call that a bias and a variance term, because we're going to talk about how much does f hat, how close is it to its expectation? That looks like a variance. And then bias turns out to be exactly the difference between the expected value and like the true thing you're trying to estimate. And we're going to talk about that decomposition a little bit because it's useful in some cases. And then we'll talk about this thing called regularization, which is like a more continuous way to scale the complexity of your function class. So instead of having this discrete p polynomial like degrees, we can now continuously kind of smoothly change this. And yeah, so thank you, and I'll see you on Tuesday.